started. Uh, Thanks so much for the presentation. We do have quite a few questions. One that was posed was when talking about cybersecurity and cyber resiliency, we use terms like mission assurance and systems engineering. How about mission engineering?
So I'll take this question on. I'm actually going to jump way back up to the beginning. This particular picture here, and I'll talk about right now in the mission engineering sense, one of the key things, at least from the Defense Department's point of view, that they're having to work through is for each system that they operate, how might vulnerabilities compromise their mission objectives, and how would those link down to standard operational tasks. And so the mission engineering component of this is actually doing that resilience analysis at this level. And then we're working back up through the bottom in the space. So one way to think about mission engineering is we build capabilities into the system that allow missions to be accomplished, but we also build capabilities in the system to allow resilience to occur in mission operation using these mission-aware modes. And so the key here is to capture that into models that can be linked back up to the formal mission engineering baseline.
He says, in major aerospace companies, all three functions are performed by groups within a systems engineering organization.
Yeah, so that was my chart, but I'm going to ask Tom to answer that because you spent a lot of years in major aerospace corporations and I haven't. So your perspective is probably better for that question, Tom.
Yeah, so they were. So the red team is typically part of the security engineering group that's in the system engineering organization, but they're generally not associated with the actual system engineering design teams. Whereas the operational risk assessment is normally part of the system design team, system engineering team, using specialists in that field in the space. The key thing that I think is not done enough is that those groups of people, so you can call them architects and then specialists in operational risk and then specialists in vulnerabilities and cyber attacks, they don't get together often enough throughout the design process. And so ideally this methodology will help them do that.
James posed the question, how does the Sentinel know which GPS is correct?
Yeah, it's a great question. So I gave the example of the UAV, and we have a Sentinel that's monitoring the outputs of the two GPS units on the aircraft. And the answer to the question is, well, we won't be sure that either one are correct. So a lot of the concept behind mission-aware resilience is that we're trying to make life much more difficult for the adversary, but not necessarily in all cases trying to prove that the adversary couldn't attack, say, both the GPS units. But if we see them agreeing, then we're making the assumption that both of them are correct. If we see them disagreeing, then we're making the assumption that something has gone wrong. And then the question is, do we use one of them for the resilient mode, or do we do something completely different? And so your question, which one do we assume is correct, is super relevant if we're going to rely on either of the GPS units after a cyber attack. But we might not do that. We may switch to another way of navigating or another solution entirely, like immediately landing the aircraft or blowing up or something like that.
And I'll just second what Peter said. I mean, the point of this design process is raising the bar in terms of cost and likelihood that attack will be successful. And so if you do this throughout the design process, then you're building a more resilient system. But again, there's not going to be any guarantees that people won't get into the system.
Right. But you can think of it in one way that we often describe it as reversing the asymmetry, right? asymmetric advantage is usually to the attacker. Here, if we can go in and put these sentinels in various key locations, now we're forcing the adversary to understand not just our basic system, but also these sentinels, and gain control of, instead of one GPS unit, for example, 2, right? So it's an exponential. You do that in a number of places, and you can quickly get an exponential multiplication of the headaches that you're providing to an adversary. Again, that's not the same as a provable guarantee.
It was more of a comment from John saying that that's diversity as a resiliency design approach.
Yes, it is. That's one of our design patterns is diverse redundancy, and it's not the only one. There are many other ways in which you can do things, but that's a simple and easy one to consider as an exemplar.
Yeah, and one of the goals of this research is that we actually build up model libraries of these resilience modes. So you can build up standard functional models, and in some cases standard physical models of these approaches that can be captured into your overall system model.
So can you please compare your approach to the DARPA High Assurance Cyber Military Systems HACMS program?
So HACM specifically focused in on the formal modeling side, the test phase of things. They used AADL, which is a domain-specific language that describes computer information and scheduling flows through the system. They used SysML to describe the high-level structural architecture. So the same way we've used SysML here in that space. The benefit of using AADL is then they could actually model the assurance cases as formal language against the domain-specific model of the computer that was running the software in that case. And then they could use that to auto-generate code in the space. So, so these things fit together. We don't have a tool right now that actually implements this systems meta model the way we're building it here in conjunction with the AADL tools that allow them to do the formal validation, but those things could be created. So, so we didn't do that original work, but we're quite aware of it.
When considering systems of systems, resilience may be defined differently to cyber physical systems. How would you propose achieving resilience across an SOS, which will have a diverse set of stakeholders, each with different perspective? So it's a great question. System of systems is a challenging framework in which to operate. So we've done some experiments and a little bit of pilot research on the idea of actually seeing how, if we were taking a systems only view, we could end up building in various kinds of resilience mechanisms. So Sentinels, for example, that are monitoring the outputs of sensors in a sensor pod. And then when we take a collection of sensor pods and use them together in the context of, say, a defensive kind of scenario where we're using the pods to detect attackers or intruders in a physical sense, then that opens up an attack for the system that didn't previously exist. So by attacking a sensor pod, you can trigger the Sentinel, and the Sentinel will end up doing something that might open up, and it will protect the integrity of the sensor pod, but not necessarily the integrity of the overall mission. So even taking relatively simple systems like that and putting them together in the context of a larger system can raise issues like that. So I'll offer that as a statement of, yeah, this is an ongoing research area. I don't think we know all the answers. I don't know, Tom, if you want to add anything to that.
Yeah, I'll say MBSE is not necessarily the solution, but you can absolutely model this in a model-based system engineering environment. So our test case of a pipeline, so there's different pipelines controlled by different organizations, and they're built from different pieces of equipment, and they come together as different route segments. And so you can effectively model all those different components and their different strategies in your system models in the space. What you can't do is guarantee that each different combination of assets that are provided by different vendors are safe in the same way in that space. And so, but you can model things like, for instance, maintenance strategies and other monitoring strategies that are consistent across the whole model. And so it allows you to take those decisions into account. But MBSE is very helpful.
How are you using the hazard analysis from safety communities for use in security?
Yeah, so we're using the STPA process, and we use that to identify the requirements and from a functional perspective that the users care the most about, and also get an initial view of what should be the control structure that we're really modeling in the MBSE. So I think that was covered in the slides, but I can go into more detail offline on that.
You mentioned you surprised at the description of CONOPS as a document. It seems this would be a prime candidate for a model, thinking of SysML activity diagrams or BPML choreographies to make it much more easily comprehensible.
Yeah, so so there's a challenge in a complex system of systems to get the description of the operations from the blue team into something the system engineers can get their arms around and model. And so we found that was a narrative process. We found we were taking the attacker's point of view too, so we were trying to actually model the system based on research on open data. So like data sheets on pumps and pipelines can be easily found on the internet, and you can easily describe the operations of the system like that. So it was a good place to start. Take a CONOPS document down through the major operations and use cases, and then in process hand that off to the modelers so they can look at doing that. In a previous projects, we've done more what you might call simulatable CONOPS, so use Simulink or some tool like that to build a real operational model that then can be linked in with the other models. But in the upfront human process, the CONOPS document seems to be pretty useful. And I think, Philip, your second question, integration with software such as code generation, I think that's really where, if we could get a project together where we linked into the HACMS program and its code generation tools. So you take the this model and you would link into the AEDL model for those computer processes, then you could build a code generation segment out of it.
Yeah, and that line of thinking, you know, sort of begins to cross the boundary between, are we thinking of resilience or defense? And sometimes it's useful to not make a distinction between those two, and other times it is, you know, it could be very useful to think about, well, I'd like to make, I'd like to just make my code better so that I'm harder to attack, right? Yeah. And Satya, does validation have no role in MissionAware model? What is the maybe you could elaborate on that question a little bit.
Yes, thank you for this nice presentation on resilience methods. My question is like, when you are doing this modeling, how do you validate? How can you ensure that this can work?
Yeah, it's a good question in terms of you know, we can use ordinary systems engineering validation methods to look at You know, whether the we think that the Sentinels and the reconfiguration operations are, you know, are potentially going to function in the way that we hope. We can take that. I mean, I guess if you really want to think about validation and how things end up playing out in an operational sense, then that ends up raising all kinds of issues. So Tom right now has got the chart with the Sentinel on it, and do you see the human sitting up there? So that's one point that I wanted to raise, that the notion that if you're thinking about validity from the perspective of, you know, I've made some kind of, I think I've made life more difficult for the adversary. I think I've made my system more resilient. But do I really have an understanding of the cost? I made certain kinds of assumptions about what it would cost in terms of implementation. That's okay, but also in terms of operation. And you know, how is a system like this going to operate? Is it going to be in a manual, in an automated way, where the Sentinel's in charge of changing system mode of operation, or are there people involved? And then what does validation mean in that context?
So one of the things I think, and this is an area where we've been trying to do some more research, obviously what we've done so far in validating these systems is attack the real systems that have these Sentinel patterns employed against them. So using red teams to do the attacks. But the potential is there to attack the model, or attack a simulatable version of a model, particularly if you get to the point where you have full digital twins of these systems. And so you know, we're trying to explore some of those concepts, linking it into the process.
Yeah, I think
Thank
that
you.
ties into Jennifer's question later on. At what point in this process would validation take place, which you kind of mentioned, and which of the three teams would be responsible for producing it?
So I see Jean has a question: who's your Army transition partner? And the answer to that is principally CCDC-AC, the Armament Center at Picatinny Arsenal. So we've done this with this whole methodology with a couple of their weapon systems, including a weapon system that we call Silverfish, which doesn't really exist in the Army. So our Silverfish is based off of a real Army networked munition system, but we've deliberately made it a bit different. So it's a hypothetical design stage weapon system. That allows us to publish openly. So you can read the SERC reports and read some of our papers that talk about Silverfish. And then what CCDC-AC has been doing is adopting this methodology for some of the work that they're doing internally, and that's an ongoing process.
How does the STPA process relate to standard DoD approach to hazard analysis?
I don't know, Tom, are you more familiar with the standard DoD approach to hazard analysis than me?
Yeah, so STPA can fit within that. DoD generally works to identify hazards. The difference between STPA and what people traditionally do in assurance analysis is traditional assurance analysis looks at things as causal chains, so a propagation of a hazard through a system, whereas STPA looks at things as hierarchical control loops, so propagation from one level of control to another. So it has a different focus, which leads to this concept of an unsafe control action. But in general, outside of that, the terminology is the same in terms of loss and hazards in that space. So I don't think there's anything that's incompatible. A lot more programs have started using STPA because of the complexity of systems and things like cyber threats, where causality has become fairly difficult to determine.
Juan had a question, where to find more information on the MissionAware part from slide 18.
Slide 18, which one is that, Tom? Okay, yeah. So we have kind of published various elements of that relate to this, but not the whole thing together. That's an ongoing publication effort that'll be out shortly. If you send me an email, I can send you the kind of stuff that we have right now, which includes some SERC reports and some published papers, and then there are more papers coming shortly, and more SERC reports coming shortly that really speak to the new meta model that we have. So that's the part that is not fully published yet.
Yeah, so the historical reports, if you go to the SERC website under research programs and look under trusted systems, then you can find all the past research reports, which take you in detail up through the whole cyber requirements process. The meta model, that part of it, I don't think there's a fully published report on that yet out there on the link, but we can send you more data.
So, Mimi, did we miss another question from Philip about DT versus OT, developmental testing versus operational testing? Yeah, we're extremely, maybe we should talk offline, Philip, to get into that topic, but we're very interested in developmental testing and hope to be getting some efforts going in that regard, but we're still working through the contractual process. But yeah, in fact, we would like to take some of the work that we've done for the Army and look at it as if we were, as if we were building the real on that hypothetical weapon system, as if we were building the real weapon system, and think about what it means to provide the developmental testers with enough information that they can actually structure appropriate tests for understanding resilience. So that's a topic of great interest.
If resilience deals with disturbances, what about non-known disturbances?
It's a good question, and I'll just say that the perspective that we adopt really is that if you're thinking of disturbance as a kind of attack or influence on the system that could lead to bad outcomes, we're sort of conditioning that those are going to occur, and we're agnostic of how they occur in some sense. And that what we're really focused on is catching things at the functional level to make sure that the key system function is preserved. And that may mean that we don't have to know all the ways in which things could go wrong. We do have to know what we care about in the end in terms of functionality. It looks like, Tom, you've moved to a slide, so.
Yeah, and I'll also say, I think from the perspective of design, the types of threats that can disturb the system and the type of disturbances you can see, and then the patterns that you would employ to prevent them are not a small number, but they're not a huge number. And so the idea here is actually to think through the patterns that produce resilience in a system as you go through the upfront modeling process, because we're not going to ever be able to predict every threat and every potential disturbance in a system in that space. The good part of that is usually if you employ a design pattern for safety, it's the same design pattern for reliability, it's the same design pattern for safety, or it can be, or at least they're similar. And so you can get a sort of economies across those domains.
So John, our good friend John Wade has asked a question: what are the vulnerabilities in the Sentinel? Can it be made so simple if it is responsible for mission intervention and redirection? It's a great question, and I see Scott Lucero has commented that this is an interesting trade-off. Significant intervention should be confirmed by operators, which minimizes the complexity somewhat. So it's a great point that don't put too much on the Sentinel in terms of automated response, right? Maybe it's enough that it handles detection and makes some suggestions, But the interpretation of what one might do, given that we think we're under cyber attack and these are the options in terms of switching modes of operation, maybe that, maybe those have to be evaluated in the context of a situation. And we want, and potentially want, an operator involved in that who can make the kinds of trade-offs. So we've been studying those kinds of issues with UAV pilots. We did this at Creech Air Force Base and now at AFIT, trying to understand how people might interact with the automation. In a, hopefully we can get to a symbiotic kind of relationship there, so that we're understanding what the potential trust issues are. We're assigning roles appropriately to the human and artificial cognitive agents, and and working through it there. On the hardness part, so yeah, if we have a really simple Sentinel, we can make those extremely hard, and we've demonstrated that with a full-on effort where we built the Sentinels with kind of lockdown, formally validated, formally verified code, and implemented in hardware that was really special in the level of protection it provided. So the Sentinel became extraordinarily difficult to crack, but it was a simple Sentinel, and it's just several hundred lines of code.
Are you?
Good.
Thanks for this, very interesting. What I was asking was, where you start is as people are generating requirements, correct? So it's pretty early in the development phasing. How do you see this happening through the rest of the life cycle of the product?
Well, so I think it would be really nice if you think of a DoD context, if the government was actually generating these patterns very early in the program phase up front as they're developing their models. So you're starting to build that knowledge base, and then you repeat throughout the design process and into test. So the benefit of capturing it into a model is obvious in that space, but you'll see it as a continuous design process. The trade that you have is that generally the selection of a resilience pattern is something that you've got to freeze as you move from architectural design into system design in that space. And so that has to be defined fairly early on. The Sentinel patterns, the monitoring patterns, if they can be general enough, and you can consider them to be, a subsystem to do that, those are generally captured in software and can be reprogrammed over time in the space. So that's the idea, is you actually, what we wanted to do is have this just be a normal part of the system modeling process as it proceeds throughout its life cycle.
Thank you. It's just hard to figure out how this factors into the cycles that we have today with so much, stuff moving so quickly. If you look at something like the T7, right? They went from concept to flying in 3 years. And, how is it that we can facilitate doing it fast, right? And doing these pieces. So clearly doing it very early is important. I'm trying to just figure out how that factors into the emerging design, especially since you're likely to have specialized missing components join at different points in the design, right? They're going to be a black box for a long time until you pick the right one, right?
Yeah. So if they're doing hazard analysis, this would integrate right in with that process. And one of the things you're doing with hazard analysis is at least up front, you're trying to prioritize what parts of the system are, you can say, safety critical or mission critical, and it would fit in with that process too. The formality of it allows you to set those priorities. And so it would also integrate with things like program protection. So identifying, a piece of software you want to bring into the system or another piece of hardware, you can see in the system where that comes in, and you can link it to these threat and resilience patterns in your model to understand what your risk is. So, we haven't done a program at that scale, but I think it kind of flows right into the normal process you would follow.
Any thoughts on how traceability to requirements management would tie into this process, with a follow-on of saying, you mentioned targeting SysML version 2.0. What added benefits do you anticipate from seeing that?
Yeah, from the SysML 2.0 framework, yeah, quite a lot. And I guess, we might want to have an offline conversation about it, but I would say that that if we really want to be able to think about SysML as becoming more than a collection of diagrams, right? To become software, relational databases that that can take a life of their own and support things like simulation. That's what the kind of thing that we're looking for, and the ability to describe processes of systems in a way that goes beyond what is capable, what you can do in SysML. I don't know if Tom, if you want to add anything to that.
No, I mean, the process, and I pulled the slide 21 back up, the process is defined to generate requirements, at least from the hazard analysis side. So those particular constraints, but they link into your model the same way any other requirements would link into a SysML model. That space, and they would be traceable the same way. So the construct of a requirement is still captured in the process.
Have you already implemented this process on the field? I'm worrying about the high amount of concepts added by the mission awareness part compared to those already in the Vitek core meta model. Do they add a very high amount of engineering work? Yeah, so in terms of what have we done in the field, yeah, we've been working with, as I mentioned, the hypothetical Army system, and have gone into great detail in that one. It's a hypothetical system. Tom's oil and gas pipeline is also hypothetical, and we're looking for partners where we can kind of do this end to end on real systems. It does add a lot to to think about anything that's model-based systems engineering. In the end, it is potentially labor intensive, as maybe a nice way of putting it, and a bad way of putting it is a bottomless pit, right? And so we think, and we'd like to play this out fully on a real system, that that the scoping, that staying close to the identified hazards and strictly limiting those will help us a lot in managing the complexity of the modeling effort.
Yeah, and Peter, I'll just say, having been through this process, that the engineering to build your model in a model-based system engineering environment and actually build your functional flows throughout the system, which is the core engineering work, is the hard part. Actually linking in the resilience patterns and the loss patterns and those things into the model is not a whole lot of additional work in the system. It's kind of part of the standard thinking process, yeah, as you're developing and reviewing the model. So, the modeling part of it, the meta model, is the natural approach to do this without a whole lot of extra work in that space. What I've always found is being the extra work is the arguments between the safety and security people and the engineering design people when they aren't operating in the same model, that negotiation process. And one thing that's really nice about this approach is it happens in the modeling process. So you can see these things, get built into the system as you go along. So that's a good thing.
So, yeah, let me just add that, there is an aspiration that we perhaps we could benefit from model-based systems engineering that was already done if we were, for example, thinking about a legacy system that may have already been done by others. That's something that we haven't found an example where we could benefit yet, but still have hope. Joe, yeah, I can read Joe's question. Resilience, security, and safety requires detectability. How are you addressing process sensors that have no cybersecurity or authentication? I will be giving a presentation to the NCOSI SIPR Thursday, April 9th at 3 p.m. Eastern, where I'll be addressing these types of issues. So Joe, I'm going to come to your talk for sure. Yeah, it's an important point because yeah, right now, what we can offer if we have no statements at all about yeah, about security or authentication for our sensors is we can offer design patterns that say, well, I'm going to force you, the adversary, to attack 2 or 3 or 4 or however many we want of these sensors simultaneously. That's the design pattern I mentioned as an example. So we do have some ways of dealing with that. But if we can combine the design patterns that we've been thinking about with better ways of managing the sensor information and building some security into those, then, as Forrest Gump would say, that's one less thing that really cuts down on the kinds of things that we might be worried about. So I think it's an extremely interesting question.
Yeah. I'll mention as we went through this process looking at oil and gas pipelines, so one of the countermeasure patterns that is fairly effective in the pipeline setting is just to increase your maintenance cycles from once a month to once every 3 or 4 days if there's a known threat. I don't know that that's necessarily a long-term solution, but it counters a number of the threat scenarios that you might run into in this space. So the kind of the point here is we know that many of these assets are vulnerable. We need to monitor them at the behavioral level, and we need to understand the countermeasure functions at the full system of system level in order to know that they're safe for most conditions.
And Joe, you're able to speak to this directly, but we actually had a follow-up question in the chats about the presentation you were giving, if it was at the IEEE NCOSI NDIA Systems Security Symposium, which was canceled. So,
no, it's next Thursday. This is the monthly NCOSI SIPR meeting, but this is something that crosses every single infrastructure because, can you bear with me 1 second?
Sure, of course.
Maybe we can get Joe to paste in a link or something to his talk into the chat here. Would that be helpful?
Good. I've got your number. I'll call you right back. No, what's happening is every single process uses pressure, level, flow, temperature, voltage, current. And that's where we have no confidence in terms of knowing, is that really a correct, or is it coming from the right place? The other that makes life very difficult is you can change the characteristics of the sensor. So you can change things like span, range, or damping, which you won't find by quote unquote comparing it to other values, because you're talking about, you just defeated safety. This is a very difficult, very big deal. I came out of commercial nuclear plant safety. And that's why I was so concerned about cybersecurity and the safety of process sensors. And it's just something everybody assumes is good and works up the chain from there.
And Joe, how's it handled in the nuclear community?
It isn't.
Okay.
It's assumed that it's there, because here's the other thing. I'm really dealing at, in a sense, the analog level, because you measure an analog and then it gets converted to digital. What people do is start looking at the digital or at the Ethernet packet. I'm there before it happens.
Mm-hmm. Mm-hmm.
And this is really not so much assuring cybersecurity, it's really assuring reliability and safety.
Mm-hmm. Mm-hmm.
And
so Joe, one of the discussions, we had a presentation last week from some folks at General Electric,
yeah,
that were using a digital twin.
right.
I don't know, have you seen their digital ghost program?
Yeah, yeah. In fact, I gave a presentation at GE Corporate in September. The digital twin, nobody is really addressing this. This is the input to digital, the digital twin.
Yes.
And here's the problem for every digital twin. The analytic digital twin assumes ideal conditions. What happens with the actual digital twin is you're subject to, if you will, the drift of a sensor or whatever else. So you'll never get, I shouldn't say never, but almost never get an absolute equality between the digital, or excuse me, between the, if you will, the analytical versus the actual. That's also why people like AspenTech, who've had these, first principles models for years, have always been off some, because we don't have a way today in real time to be able to say, is that sensor really correct?
And so we're not going to disagree with that. I mean, it's the challenge of modeling, and it's the challenge of real systems. And
yeah, it's just the intersection that's been ignored.
so, so we're trying to address the fact that people are not considering security in their upfront design patterns. So the system as a whole is unprotected. You're not necessarily going to be able to protect every component of the system.
No,
but at least you can come to understand how they will affect the system.
Yes.
Design process.
Yeah, and part of it is, when I first started dealing in this, that was a whole lot of years ago. We didn't have the machine learning and the AI that's available now. So part of this is, how do we start bringing some of this modern, technology all the way down to this lowest level, in a physical process.
Yeah, you're exactly right. And AI, since it works in model space also, having these tools at hand are the key, you can call it foundational aspect of getting those capabilities into these systems.
Yeah, and the beauty is, like I say, this isn't cybersecurity. This is really reliability, safety, resiliency, with cyber coming along for the ride.
Exactly.
Mm-hmm. Mm-hmm. Good, and thanks to Scott for posting a link to and instructions for your talk, Joe.
Oh, thanks.
And Joe, is that talk open to the public?
Yeah, I think so.
Perfect. In that case, I'll include the meeting details that Scott provided into the chat as well.
Please do, because, I've got an article that's going to be coming out in the National Society of Professional Engineers magazine. And what it's really about is, we can't solve this problem without a team effort across the board. And there's also been little, if you will, coordination between all of these different groups that are, playing around this very big elephant. I happen to be heavily involved with ISA, the International Society of Automation. There's an SAE committee, G32. You've got in COSI, you've got, there's a standards body in the UK, IET, that's doing something similar. This is in the area of integrating or, the cross correlation of security and safety. How do we not do inconsistent things?
So Joe, there's a question from Lisa Murphy that maybe you want to answer actually. Can some of what you're talking about be addressed by having a distribution associated with the values coming off the sensor? So characterizing, I assume, I take that to be, characterizing the uncertainty of the sensors and using the, following the design process to recognize that uncertainty. What do you think of that kind of view?
Well, that's what we did for years and years and years. I mean, that's the standard way you look at sensors, you look at uncertainty. And then what happened, and this is why I'm so sensitized, is a number of years ago, we found a common cause non-detectable failure in pressure, level, and flow. And the most popular pressure sensor vendor in the world. In fact, it's in the Smithsonian as one of America's top 100 inventions. And it turned out it was a manufacturing flaw. So that defeated all of our, if you will, probabilistic models.
Mm-hmm.
And that's the other issue going on with cyber or anything malicious. That'll defeat any probabilistic model. It's a really hard problem.
Mm-hmm.
And what do we do with our hundreds of millions of process sensors that are out there today? And that includes at DoD. A ship is a power plant with rudders. I've asked, the National, Academy of Engineering, this is really a grand challenge. What are you going to do?
And Tom, thanks for flipping to it. Just a save the date to discuss this and more of our SERC research at the SERC Research Review. The dates are still set for November 17th and 18th. And then Tom, on the next slide is our next SERC talk, which is with Dr. Martin Torgren. How do we make sure future cyber physical systems are human-centered and in particular trustworthy? And that will be taking place on Wednesday, June 3rd. Jern, we hope you can all join us for that. I'm sure there's probably more follow-up that'll come our way. So please feel free to email myself or Barry or visit the SERC Talks page with the contact information that will go both to Peter and Tom. Thank you again for joining in. And again, big thanks, Peter and Tom, for sticking out.
Thank you, everyone.
Yeah, thanks everybody who stayed on late.
Mm-hmm.
Thanks. See you at the next one.